everybody, welcome to the first Math Club talk of the semester. Today we have our own Tyler Johnson, who's a fourth-year math major, who's going to be presenting his research. He did his RU, University of Washington over the summer, including the Dirichlet Problem. Please join in welcoming Tyler Johnson.
Thank you for the lovely introduction, Cody. So, first, I'm going to pronounce this Dirichlet. I've heard all manner of professional mathematicians pronounce it different ways. I've heard it Dirichlet, Dirichlet, combinations of those syllables together. But yeah, so Dirichlet. So first, we're going to work on the Dirichlet problem on a discrete electrical network. So does everyone here know what a graph is? And not a graph of a function, but a graph, the combinatorial object of graph. No?
No.
Okay, all right. So a graph is just going to be a set of points in a plane, and then some edges between those points. So here's an example of graph. So in general, a graph G is some set of vertices along with a set of edges, where your set of edges is a subset of V cross V. So we specify an edge by specifying its two endpoints. And this is, we don't care how it's arranged in the plane or anything like that. It's pretty much just a discrete combinatorial relation. So, all right. Now, does anyone here know what conductivity is?
You mean like with electricity, like with
right.
wood?
I think we're a bunch of double E majors. What is this?
Okay, so conductivity.
You know, look at like wood, not conductive.
Right. So conductivity is a measure of how easily electrons can flow through some sort of substance. So in particular, it's the reciprocal of resistance. So I'm going to define an electrical network by taking a graph, and then on each edge, I'm going to specify some sort of conductivity. So you might think these nodes in here, these vertices, are resistors, and we've got we've got wires perhaps made out of different substances connecting them. So this is, so it's electrical engineering basically. And then additionally, we're going to specify some interior nodes and then some boundary nodes. So your boundary nodes, boundary vertices, I'm going to denote them by filling in the vertices they're at. So basically, the designation of whether it's an interior node or a boundary node is a designation of whether or not current can flow into this graph. So at these nodes, we can let current flow into this electrical network. And we've got these conductivities here. And so based on some sort of electrical potential, the electrons that come into these nodes are going to flow in to this graph through these nodes. So does everyone has some sort of an idea? Yeah,
so would it be sort of like you attach the electrical leads to those two nodes?
Yes,
Okay,
exactly.
So, and you're not allowed to do it on the ones except on the boundary.
Yeah, so the boundary are the only ones that you're allowed to do that on.
So one's in and out. Does it flow through? From boundary to boundary? Can you have three boundaries?
So yeah, so it can also flow out of the boundary.
Okay, so
but you need not have
It's just all nodes of degree 1?
No, you can also have this.
So
you just designate them. You just pick what.
Yeah, you just pick your boundary.
So it's no property of the graph.
No, it's not a property of the graph. It's a selection to determine the electrical network.
Okay.
So that's a conductivity function gamma from the edge set of the graph to the positive reals, because conductivities have to be positive, and that's just a distinction that we take. Does anyone know what Ohm's law is? Okay. All right, now people know. All right, so Dave, what's Ohm's law?
Voltage equals current times resistance. Sorry. Yeah, that's right.
Voltage equals current times resistance. So let's say we had some sort of so the reason that electrons flow from one node to another is because of the potential difference between these two nodes. We've got to build up a surplus of electrons over here. We've got less electrons over here, and so they flow across to get to, they follow the path of least resistance. And so if we have some sort of potential function on the nodes, so let's say we have a potential function u, which is on our nodes, our vertices of the graph, to the reals, then what we know is that the current across an edge PQ, where here's P and here's Q, by Ohm's law is going to be equal to, I said conductivity is the inverse of resistance, the reciprocal of resistance. So it's the conductivity times the difference in the voltages. Okay. So, yeah, so this is just the same that electrons flow from regions of high electric potential to those with low electric potential. And so now we're saying that we're also imposing that no current can come into the middle of the network. No current can come into the interior of the network. So that means that all of the current flowing out has to, so current can be positive or negative, but all of the current going in or out of the node has to be 0. So the sum over the current of PQ, where Q, and I'm going to say Q tildes P, if Q is connected to P in our graph. So this is equal to the sum of gamma PQ, where Q tilde P, P minus PQ, and this is equal to 0 if P is in the interior of our graph. So I'm going to denote my non-colored in nodes by interior, int for short of G, and my colored in nodes, my boundary, by del G, which you guys have seen some manifolds, you know why I use that notation. So, alright, so this is essentially a condition that there are no sources or sinks within the interior of G. And we say so this condition is dependent on our potential function U. And we say that if this condition holds for all P inside of the interior of G, then U is gamma harmonic. So now, more basic circuits. Does anyone know Kirchhoff's current law? Anyone? So Kirchhoff's current law is just that the sum of the currents at any point, the currents going into, so it's we've sort of covered it already, but the currents going into any point is 0. And so that's true for our boundary nodes as well. Anything going in has to come back out. So,
yeah, so you're being a little confusing about currents versus potential. You were sort of saying originally at the boundary you could apply, you could put batteries there, you could apply an electric potential, but then you sort of went on to suggest you were feeding current in there.
Right, so right, so we apply, yeah, that's right. So you apply a potential to the boundary, and that induces a current. Sorry. Okay, so now let's let phi of p be the current flowing out of any point p in the graph. So in particular, we said phi of p equals 0 for p in the interior for a gamma harmonic function u. Okay.
By flowing out, do you mean?
So flowing negative current can flow out, and
Right,
thus really
okay.
that's current flowing
right,
in.
That was my question.
Yes.
Okay.
And so Kirchhoff's current law says that the sum over all p in the vertex set of G of phi of p is equal to 0. Okay. Since we already know that phi of p is equal to 0 for p in the interior, this is really just the statement that the sum over all p's in the boundary of G of phi of p is equal to 0. So now it can be shown that, and we will show that. Tell you what, I'm going to move this board up now. Is this the ideal move? Alright, here we go. Okay. So now we're going to show that if we specify the electric potential on the boundary, we have a unique gamma harmonic potential function on the entire graph. So let's do an example for what that means, just so we can see concretely. So I'm going to say, let's take this graph. So boundary is here. Once again, the boundary doesn't really have to be realized as any sort of physical exterior of this graph. It's simply it's an arbitrary designation. But so we'll specify potentials on the boundary. So 1, 2, 1, and 2. And then 3, 1, 4, 2, and 1. So these, the numbers that I've put near the edges are the conductances of the edges. So this might be made out of, something like iron or something like that, and this edge might be made out of something like copper, something more conductive. What's up, Dave?
Question about boundaries. Can you have, really it's a nice question, can you have leaf non-boundary nodes
What's a leaf?
in the graph? Like a degree 1 non-boundary node?
Non-boundary node. So yeah, this is fine, for example.
So like on the graph that you have there, could I add another node out to the right and have it not be a boundary?
Imagine such a node wouldn't get any current.
Right.
Right, yeah,
Okay.
so that's the problem with that is,
Okay, yeah.
yeah. So you can do it however you want.
But,
However,
yeah,
you're going to come up with some trivial examples. So we've got these conductances and these potential values on the boundary. So I want to find what the potential U1 is at this node and U2 is at this node. So such that the entire potential function is a gamma harmonic function. So that's the condition that, what do we say? That the sum of the gamma PQs of UP minus UQ is equal to 0, where we're summing over all the Q's that are connected to this P, or not connected, but are neighbors of this P. So the first part is that So looking at the sum over this node, we have that 1 times u1 minus u2 plus 2 times u1 minus 2 plus 3 times u1 minus 1 plus 4 times u1 minus 1 equals 0.
I'm confused.
Alright.
So you're using subscripts.
What's that?
What are U1 and U2?
So U1 and U2 are the potential,
I'm sorry.
potential
At the
at
non-boundary
the
point.
points.
There only have 2 non-boundary points.
Yeah,
Okay, I got
right.
it.
We have 2 non-boundary points. So is everyone following where I got these sums right here?
Should it be 4 times u1 minus 2?
Yeah.
Yeah. Yeah. Okay. So does everyone believe that I can solve this equation?
No.
This is,
Do you need equations for the four to represent the sum of the potentials along the outgoing, some of the currents along the boundaries?
so we're not concerned with the currents at this point. All we're considering is finding our gamma harmonic function u.
Okay.
And in general, that's the objective of this sort of problem, is to find the gamma harmonic function u. So you can certainly solve this. It's easy. But I would like to do this more generally. I would like to say that if you give me any graph, that I can come up with a solution that, well, first I can show that a solution exists, and second that I can show that that solution is unique. So here's how we come up with that solution. I'm going to construct something called the Kirchhoff Matrix. Okay. First, we're going to take an enumeration of our vertices. And so we'll take an enumeration of our vertices. V1, I ranges from 1 to n. And I'm going to specify that the boundary goes before the interior. So V1 through, say, k are going to be, Vk are boundary nodes, and then Vk plus 1 through Vn are your interior nodes. And now I'm going to define gamma ij is going to be the conductivity between the edge, Vi, Vj, if Vi is connected to Vj, or Vi is a neighbor of Vj, and otherwise, I'm going to make it 0. All right? And then, so, thus, we find that the current out of any Vi is equal to the sum of gamma ij u Vi minus u Vj. The sum of the conductance, if that edge exists, between UVI and UVJ. And so really what we're just saying is that there's an edge there with conductance 0 if there really wasn't an edge there before.
Sum over j.
Yeah, sum over j from 1 to n. Okay. So now I'm going to define my Kirchhoff matrix K with entries Kij by Kij is equal to the negative of this gamma that I just picked up. If I is not equal to j, and I'm going to say that it's equal to, for when the diagonal indices, it's going to be the sum over gamma ij, j ranging from 1 to n. Okay, so in particular, note that this is, so row sums are 0. Does everyone see why that's true? Row sums are 0.
You might want to make an example of a numerical matrix based on.
Okay, so sure, we can do a matrix. So, all right. So I'm gonna name these vertices v1, v2, v3, v4, v5, and v6. This is just a messy picture at this point, but so the sum of the conductances outside of v1 is 3, and then we note that it has no edges between v2 through v4, so we get 3 zeros, and then it has a conductance of -3 to v5, so this is -3 and this is 0, and then here with v4 we've got, or sorry, I should go to v2 next. So it doesn't go to,
Doesn't go to V1.
doesn't go to v1, so we've got a 0 there. The sum of the conductances out of v2 is 4. The only one it hits is v5, so it's -4, 0. Then we've got v3, which is going to be 0, 1, and then it hits, the only one it hits is v6, this is -1, and then for v4, we've got zeros, a 2 on the diagonal, and then v5, so we got a -2 here, and then, so here, this, so v5 has a conductance of 3, or -3, 3 going to v1, -4 here, right?
It's not that the conductance is negative, but that's your kappa thing, isn't it?
Right, yeah, it's negative the conductance. Then
It doesn't touch the other
v3,
0.
yeah, so there's a 0 here, a -1 here, no, -2. The sum of the conductances outside, so that's 6, 10, 10, then v6, it's got conductance of 1, and then 0, 0, -1, 0, -1, 2. Right. So one thing to notice is that this matrix is symmetric, and that just comes from the symmetry of gamma ij. And in particular, we can decompose it into a block matrix, where, so I'll go ahead and draw the decomposition. So v1 through v4 are interior nodes, and then v5 and v6 are exterior nodes. So, right, yeah, so this is the boundary, this is the boundary, here's the interior, here's the interior. So in some sense, this captures all the information about the interboundary activity. This captures all the information about the inter-interior activity, and this captures all the boundary interior information. So, K is a symmetric matrix of the form A, B, B transpose D. And A transpose and D transpose, or A and D have to be symmetric, obviously. So now let's look at, so let's write, I guess I should move towards again. So if we look at our conductance function u. We can write this as a vector, really, where we just list out its values at each of the vertices as we enumerated them earlier. So it's uv1, uv2, vn. So this captures all the information of u. So if we look at what the Kirchhoff matrix applied to this vector u is, and look at the ith component of that, well, what we've got is this is going to be the sum, right, so it's the sum of the kappa ij's, kij's, uj, from j equals 1 to n, which turns out to be the sum of the gamma ij's like times ui. So just looking at the diagonal entry, or the term of the sum with the diagonal entry, minus the sum of the gamma ij uj's. Okay?
So that sum is where j doesn't equal I.
Right. Over j not equal to I.
J
Okay?
equals I is okay since that node is zeroed out for I equals j.
Oh, I guess so.
Gamma I is 0.
Right, but okay.
Oh, yeah.
But so this is just the sum of gamma ij of ui minus uj, which is, as we said earlier, this is going to be the current flowing out of ui. So that's nice. Is everyone following since from the Kirchhoff matrix onwards? Is anyone totally lost? Okay. Alright, cool. So remember K was equal to ABB transpose D. So if we decompose U into boundary data and non-boundary data, so this is decompose into two subvectors. Let's say the boundary data is f, so these are the values of u on the boundary, and some unknown stuff x. Because our goal is given f, so given boundary data about this electrical network, I want to find what the entire potential function u is. So we have that k applied to u is equal to k applied to fx, which is equal to the current flowing out of the currents at each of the points in the network, which we said on the interior was 0. So if we decompose this, because of the way we constructed K, and the fact that this is interboundary stuff, this is inter-interior stuff, and this is the cross stuff, we get that this is equal to the current on the boundary and the current on the interior, which we said the current on the interior was 0. So we've got some stuff up here and then 0 in the bottom. So K was equal to A B transpose, or B transpose D applied to Fx. So we can just do block multiplication by like regular matrix multiplication. So this is AF plus BX B transpose F plus DX. Since we know this bottom component is 0, then we have that B transpose F plus DX is equal to 0. And if we knew that D were non-singular, then we could say that X is equal to D inverse B transpose F, which gives us our entire potential function based solely on the boundary data. And it turns out that it always is the case that D is non-singular. However, I'm not going to give justification for that today. Now, all right, so we also, so this gives us a solution, given boundary data F, this gives us a solution, a gamma harmonic solution for our electrical network, for the electric potential function of our network, F D inverse B transpose F. Any questions?
Negative.
Negative. Okay. So basically, in order to find the electrical potential function, it's just some linear algebra, some matrix multiplication. Yeah?
Yeah, you don't have any constraints over what phi applied to the boundary is, the top portion of your
Right.
right side there. It's just whatever pops out when you finally solve the system.
Right.
Okay.
I imagine someone is interested in that number somewhere, but not I.
Okay.
So,
So Jada.
So we can define something called, I'm going to define something called a Dirichlet norm. The Dirichlet norm, rather, over, so it's the Dirichlet norm of some electrical potential function over an electrical network. So W sub gamma depends on, the Dirichlet norm depends on gamma. An electrical potential function U is equal to the sum of gamma PQ UP minus UQ squared over P, where PQ is in the edge set of G. So this is the Dirichlet norm, and while I'm not going to prove it to you, if you take if you restrict the boundary data, so if you require that U restricted to the boundary is equal to some function F, some boundary electrical potential F, then there is a unique, as we said before, there's a unique gamma harmonic function U on this electrical network. And in fact, this minimizes this norm here. Did everyone quite get what I said there? So if we look over all functions that satisfy this, the unique electrical potential function with this boundary data is the minimizer for this norm. Everyone good? Does everyone understand what I said there? I'm not going to give you justification for why that's true, but it is. I'm going to use it later. Right, so this is an introduction to the Dirichlet problem as it's formulated over a discrete electrical network. It's actually inspired by a really a much more famous problem, the classical Dirichlet problem, which goes as follows. Take a region in the plane, a complex plane, or R2 if you prefer. Call it omega. and specify, I want to find a function that's continuous on omega. So I want to find u from omega to r such that a couple of things hold. So the boundary of omega is, or u over the boundary of omega is specified as some function f. Boundary of omega to r, and del squared of u is equal to 0. So this is the Laplacian operator, and what it is div of grad of u. Does everyone know what div and grad are? Probably not. So u is a function in multiple variables. So grad u is going to be the vector of partials, u dxi. Okay, and then if we want to take the div, the divergence of the function, so div of a vector value function f is equal to dfx, so the x component of f, or I'll write this in general, the sum over the ith component taking the ith partial derivative. And so this is a special condition. And really, actually, I don't, well, this is the classical Dirichlet problem. I'm going to modify it a little bit. So I want that div of gamma times grad u is 0, where gamma is, again, some conductivity function on this region. So you might imagine that this is some sort of non-uniform metal, some sort of metal that varies in density. So its conductivity varies throughout it. And it varies with a function gamma, with a conductivity function gamma. And so this is actually the infinitesimal equivalent of our gamma harmonicity condition from above. And you might also hear the original del squared u formulated as u has no sources or sinks within this region. So if you've taken any ODEs, you know what a source or a sink. What's that?
Grad u has no sources or sinks.
Grad u, yes, sorry. Grad u has no sources or sinks through over this region. Right, so this is the classical Dirichlet problem. And so Dirichlet thought he proved that there is a unique continuous solution. And while he did succeed in proving that it's unique, he did not prove that it actually exists. He did not prove that it exists, and Weierstrass proved him wrong several years later, and then I think Hilbert was the one who finally completed the proof in 1900. And additionally, uniqueness is the easy part of the proof. Existence is much harder to come by. And furthermore, there's an extension of this problem where if you impose smoothness conditions on f, how smooth does that make u? So if you know some derivatives exist, some derivatives of f exist, what do you know about the derivatives of u? So using smoothness introduces more difficulties to the problem. So this is solved using something called the Poisson integral formula, which is covered in the graduate complex analysis course. It's not in the undergraduate, is it? No. But that's a big deal in complex analysis. And additionally, this problem has its own Dirichlet norm. And that is, so U is the solution if and only if it's the minimizer of this norm, U gamma squared, the integral over your region omega of gamma times grad U squared, magnitude of grad U squared dA. So you integrate the magnitude of your gradient squared times your conductivity function over the region. And the minimizer of this with U satisfying boundary data, U restricted to the boundary of omega equal to F, is the solution of the problem. Right, so at this point, most people in the RU I was working in were interested in something called the inverse problem here. And that was, so given if you're able to induce a voltage on this region, and then also induce an electrical current on this region, from that, or rather read the electrical current that comes from that reason, sorry. Can you then figure out the conductivity function gamma? And so what that's actually useful for is this idea of an electrical X-ray. So what one might do is, if you want to look inside like a cross-section of a body. So got a cross-section of a body right here. You might put a ring of nodes around me, and then induce some sort of voltage potential difference across this, and then read off the electrical current from these potential differences. And from that, doing some complicated math, you could possibly figure out what the conductivity function gamma is. And so you might be wondering, well, why do I care what the conductivity function of the cross-section of my body is? But the cool thing about that is, so if you know...
It like lets you see inside the body, like gives you sort of like an image.
Right, so tumors and muscle and bone and that sort of thing are all have different conductivities. They all have different densities and are made from different elements, and so they have different conductivities. Electrical currents flow through some slower than others. And so as a result, you can reconstruct this based on some sort of density. So you might be able to figure out that there's a what's that?
A weird body.
You might be able to figure out that there's a kidney stone or a tumor or something like that.
So the point is a CT scan, which a number of us have had or will have in our lives, is based on the variant of what you're talking about here.
So that uses the radon transform, doesn't it?
Yes.
Right. So, but uses an invasive X-ray. This is low voltage electrical currents. So if it could be successfully completed, then you would be able to. Low voltage electrical currents are basically harmless, whereas X-rays cause potentially much more damage. So that's the cool thing about the inverse problem. So now, what I was doing, let's see, how much time do I have left? 15 minutes? Okay, so what I was doing was not really quite related to this. But electrical networks are really easy to solve. This problem is, so this problem here, the inverse problem here, is much more difficult. It's easier with the electrical network case, though not always solvable. So what we would like is to be able to approximate this by some sort of electrical network. So I can, just say, take some sort of lattice across this cross section, and say all the nodes are the intersection points of this lattice, and the boundary nodes are just those on the boundary. And maybe I could use what I know from discrete electrical networks in order to approximate the conductivity solution on this region. And so that was my goal. This is actually an approximation that physicists use all the time with basically no justification at all. All the time they say, let us approximate this region by a lattice, by a thin mesh grid or something like that. Which there's no real mathematical justification for. And so
just throw without loss of generality in front of it.
Right. So I set out to do that. And so I spent a lot of the summer, I eventually got to this problem. And it took me a while. It took me a while to get to this problem. I was interested in a lot of different things. This is a I've really only exposed you guys to a small subset of what this field is about. I really haven't told you anything about the inverse problem stuff, which is probably the most mysterious and coolest stuff about it. But so it's a really rich field, and so I just spent a lot of the summer moving from problem to problem and, making some progress on one problem, but really realizing that I needed to solve this other problem before I could finish it. And so through a sequence of problems, I came to this one about approximating these regions by discrete electrical networks. And so I'm just going to give you guys, my original plan was to go, somewhat into detail with this proof, but I'm just going to give you guys a sketch of the proof. But so I'm just going to work on the unit rectangle. And so given a boundary function f on the unit rectangle and some conductivity function gamma, there's a unique gamma harmonic that yields a unique gamma harmonic function, which I'm going to call u infinity. Gamma harmonic by here. And then, so I'm going to take a grid, an n by n grid, lay it on top of the unit rectangle, and I'll call this grid Rn. And so I'm going to take a boundary function which has boundary values matching f on these intersection points here. And then I'm going to take the conductivity function for this electrical network to be the, and I guess it's probably not going to end up being clear why I've done this, but it's the average of the conductivity function. So the conductivity on this edge is the average of the conductivity function on this parallelogram right here. And so what we would like to do, so this has a solution, un, which is a function from the vertices on our Rn to R. What we would like to do is extend this in some way to the entire rectangle. And so one way to do that would be just by linear interpolation. So I've got 3 values right here. So just think of 3 values sitting out in space out here, and I can put a little plane, a little triangle on them. So we linear interpolate over the entire rectangle so that it's our UN, our extended UN, is piecewise linearly continuous over triangles, essentially. So that's how we extend UN. And what we'd like to do is show that this UN converges in some way. These UNs get really close to U. And so the nice way to do it is show that UN minus U infinity in the gamma norm goes to 0 as n goes to infinity. And the Dirichlet norm goes to 0 as n goes to infinity. And justification for why we want to do this is just because U infinity it can be selected as the minimizer of this gamma norm given boundary data. So that's what we would like. And now note that UN minus U infinity squared in the gamma norm is equal to U gamma squared plus U infinity gamma squared minus twice what I'm going to call the inner product of these two things, which is where the inner product gamma is equal to the integral over R gamma, the gradient of UN dotted with the gradient of U infinity dA. And so you might believe this based on what you typically understand the norm as, but it's a pretty routine computation to show that. Now you can use, essentially it comes down to integration by parts, which if you've seen integration by parts in higher dimensions becomes really obvious. If you haven't seen integration by parts in higher dimensions, I'm just going to confuse you by showing it to you. So from integration by parts, you can show that this goes to U infinity gamma squared. And that's basically because the boundary data of UN is going to the boundary data of U infinity. And then the bulk of the problem is essentially to show that the norm of this UN goes to the norm of U infinity. And so I spent 3 weeks straight really bashing my head against the wall trying to figure this out, and then solved it in like 30 minutes one morning, which was really cool. It was like I just tried tons and tons of different solutions, and then I woke up one morning and was eating yogurt, and it was great. But so essentially the way it works is, again, there's lots of detail to it, and it will at best confuse you if I try and cram it into the next 3 minutes. However, the way to go about it is to construct a function u twiddle n, which just as un can simultaneously be interpreted as a function on an electrical potential function on the electrical network, it can also be interpreted as a function on the rectangle. And so on the discrete grid electrical network, and also as the rectangle, the region in R2. So such that this guy clearly converges to U infinity. So you do that by taking U infinity and breaking it up over the grid. And then since you know that this guy is given by a minimizer over the electrical network, you have that UN gamma, since he's the gamma harmonic solution. This guy may not be gamma harmonic, or at least this guy is gamma harmonic over the discrete electrical network. This guy is gamma harmonic over the region R. We construct this guy so we can interpret it as a function on the electrical network. So as a result of the minimization property of UN, UN is less than UN twiddle, and then this guy, since this is a function on the rectangle and U infinity is a minimizer, we have that this is true. And so by squeeze, we see that everything works out nice, and that doesn't have any detail at all, but hopefully you believe that I'm right. Yeah, what's up?
So part of the whole challenge here was to come up with what U infinity was at all, right? That there even exists a U infinity?
So the fact that there exists a U infinity is given by the Dirichlet problem. That's just the solution of the Dirichlet problem.
Oh, okay.
It's trying to do a discrete approximation of it, to do this grid which you keep
So I believe the
refining.
I believe the UNs exist because you've told us in some detail at least that the finite version is solvable.
Right.
So you're trying to justify that the infinitesimal version is solvable?
So we know by Dirichlet that that's solvable. I'm trying to justify that the finite versions converge to, in some sense, converge to the infinitesimal version in the limit. So we can use them to approximate the infinite version.
Never mind. That makes this mean. Okay.
Okay. Does anyone else have any other questions? Does anyone have any questions about the RAU or anything else or anything like that?
Well, some people might not even know what an RU is.
Okay. Do you guys want to hear what an RAU is? Okay. So I think it stands for Research Experience for Undergraduates. And essentially, there are these NSF-funded projects which universities host, where if you're pretty good at math, you can apply to these, and hopefully you can get in, and you'll go to, for example, University of Washington, and work there over the summer on some sort of project that they've specified. And the projects vary from program to program. Mine was primarily interested in electrical networks and inverse problems. Malik is in here. Yeah, Malik was in one in Santa Barbara. Wait, no, Santa Barbara. San Bernardino, which had something to do with knot theory, right?
It was split in half. A lot of programs have like two different or multiple different kinds of projects you go into.
Right. So most people did the electrical network problem at my program, but there was also a couple people worked on combinatorics with another professor that wasn't as involved in the RAU, but the RAU is led by a couple of professors, and they're usually graduate TAs, and it's about 10 people who all work together on similar problems, and you collude with the other students if you're interested in that, or you work on your own, but it's really, really great experience. It's really cool.
We've had them here for about 6 summers, but I'm currently applying for another grant.
Yeah. So, any other questions? No? Okay. Cool.